This is a walkthrough on a project on optical character recognition. It will predict the characters 0 through 9 and A through Z as represented by individual images of those characters. I'll use Python via Jupyter Notebooks, and specifically the Keras package, to build a neural network for the identification. Finally, I'll demonstrate that using a more restrictive neural network will lead to a superior character predictions. This is part of the final assessment for CSCI S89 Deep Learning from the Harvard Extension School during the summer of 2025, and I am Nick Sanford. For this project, we're going to use the Kaggle dataset standard OCR data. You can see it here. It's composed of two folders, data and data 2. We're going to use data 2, which has training and test data sets in it. Let's look at the training set. It has a series of folders, 0 through 9 and A through Z, of images that represent that letter. So if we look at the A, we can see all of these images with the letter A. We're going to use that folder name as the label, and then we can access these images. Here in Jupyter Notebooks, we're going to start by importing our packages. Most importantly is Keras, but there's a couple other packages as well. Then we're going to access that data that we just looked at, the Kaggle data. We're going to bring in training data sets, validation data sets, and test data sets. There are over 20,000 training images. 80% of them we're going to use for our training data. In this case, 16,585. The other 20% we're going to use for validation, 4,043. And then the separately provided test data set has 3,241 images in it. Now let's look at the base model that we're going to build. We're going to use image data generators to bring our data in. So far, we simply have a link to an image file, a JPEG or whatever. Now we need to change that link to actual data. That's what the image data generator does. We're going to scale it by 255. That way, the numbers inside the image will end up scaling between 0 and 1, which will be easier to work with later. We're going to reset our image size to 32 by 32. The actual 32 tall by 32 wide. The actual images vary from that a bit here and there, but now we're going to have a standard image size. For our training data set and our validation data set, we're going to use random images, a random order of the images. When we go to predict our data, we're going to use the term shuffle equals false so that they come in order. That's necessary so that we can tie back the label of the image to the image itself. We'll see more of that a little bit later. Here we see that same count based on those different data set types. You can also see a sample of the images. This is images numbers 1 through 6 of our training data. Now they're in random order because of that shuffle mode, but you can see the label, the title of that folder aligns with the image that we're looking at. Let's go ahead and build our model. It's probably a little bit easier to look at the graphic side, the output side of building the model in Kaggle, in Keras. Our images, I said, are 32 by 32 by 3. 3 is the color scheme, which is typically red, green, blue. In our case, the scheme is all black and white, so it doesn't truly matter. But those channels, those 3 channels, we can use to try to train our model. The first step I'm going to do is to increase the channels from 3 up to 16. By increasing that channel size, it's going to allow us to extract some data in a little bit better way. Then we move it up to 64 channels. Next, I do a max pooling layer. So this is a 2 by 2 layer in this case. It looks at 4 pixels in a 2 by 2 grid. Out of those 4 pixels, you'll pick the most dominant pixel, the highest scored number of the 1 to 255. Now it's 0 to 1. Grab the largest number of that. This is going to start to eliminate some of the noise that we get inside of the image. Next, I'm going to scale it up to 128 channels. Then we're going to do a dropout layer. So the dropout layer says that we're going to randomly start to ignore certain pixels. 20% of the pixels, we're just going to ignore them. What that allows us to do is to not focus on small anomalies that we'll get in the pictures. When that anomaly gets dropped out, we can then train the model on the better part of the picture. So experience has shown that dropout layers tend to make these predictions a bit more accurate. From there, I'm going to move us from 128 channels back down to 64 channels. Then we're going to flatten it. So the flattening takes us from a length and width and channel situation to just an array of numbers, making it easier for further processing. We're going to do another dropout, and then we're going to go to our final output layer with 36 neurons. The 36 neurons represent the numbers 0 through 9 and A through Z. So this is our base model. Don't get too focused on this exact form of the model. We actually don't care about this model. We're going to be interested in the submodels that we're going to look at in just a little bit. And so it's actually bad if this model is too good, because then it's going to take away our ability to analyze the things we're going to do into the future. So let's run the model. I chose 10 epochs. You could argue for more, you could argue for less. You should train it and figure out the correct number. But again, the base model is not the purpose that we're after here. So we'll check the accuracy. You can see the graph. The dots represent the training accuracy of the model. I think it's easier to just look at the numbers. And we get up to 95.1% accuracy. That's pretty good, especially given that we didn't put a lot of effort into actually building the model itself. So let's do a prediction. Let's see what happens. And so this is representing the very first 6 images. Why are they all zeros? Because we're doing the prediction side right here. We're doing the predict, the model-based predict, and we're using the predict image data generator, which was put in order. The shuffle equals false. And so the very first images are the 0 folder, the 0 labels, and that's why all of these images are zeros. Here numerically, we see that the labels are all zeros. That's that folder option. And here are the predictions. Well, look, image number 4, index 4, image number 5 has been predicted to be an O, not a 0. It is incorrect. It's done the wrong prediction. That represents this image right here. This is an image of a 0, but the model predicted an O. So this is what we're going to focus on with our submodel. We want to see if we can improve these 0 to O predictions. So that's a nice graphical thing. Let's look at it with numbers. There were 16,585 training images, of which 15,905 were predicted correctly and 680 were incorrect. Looking at it another way, all of those 680 incorrect images, we have a top list of errors up here of incorrect mappings. The most frequent mappings, incorrect mappings, are 0 to O and O to 0. Those are by far the largest. Then we see some randomness, the 2 going to Z, 7 going to Z. Here's another X going to Z situation. So Z seems to be a prevalent type of error, and you can see there's plenty of other errors. We're going to look at 2 submodels here to see if we can improve our base model. The first submodel is going to be O versus 0. So let's look at our O and 0 predictions. Not our labels, because we aren't going to be able to recover our labels when we're actually doing this live. But we can look at our predictions. And so we can accept in all of this data, all of these O and 0 predictions. We're going to accept in these nearly 700 correct predictions, and then all of these errors. Now we're only going to allow the model to select zeros and O's going forward. And so what that means is these pieces right here, the 119, 111, we're going to hopefully correct those. Now these other pieces, Q, D, 6, I, V, these will never get corrected because they're going to be remapped to either a 0 or an O. So these errors are going to remain as errors. We're going to create a second submodel with the letter N. In a prior run of this, N was very prevalent as an error. Up here in this particular model, we saw that Z was the more prevalent issue. So for you personally in your situation, go with whatever letter is causing you problems, not with the letter N. We aren't going to prove anything with this N analysis, but the concept of it is going to hold true. So in the case of the N, we had 449 situations where it was correct, and then all of these other labels were incorrectly predicted. And so we're going to create a submodel that accepts in all of these N predictions, and it's going to allow us to predict anything at all 36 possible characters moving forward. So up above, we can only predict 0 or O. Down below, we can predict all 36. Those are the two submodels. Let's look at model 0O, the first one we're going to do. We go to our base model and we pull out all the predictions of zeros and O's. That's the data we're going to work with. Then we're going to build a new neural network model. Here it is, the graphic side of that model. This is the exact same model that we used before. That's what we're trying to show here, is that the exact same model, but with different inputs, can produce a superior output. The only difference between the prior model and this model is that we only have 2 output neurons. Before we had all 36. We only have 2 here because you can only have an O or a 0. So we can run the model and get some results, and we have 741 that are now correct. We'll look at that more in just a moment. The in model, we're going to do the same thing. Look at the base model, select the in predictions. We're going to build a brand new model for the in. This time we have 9 outputs. I told you we would have 36. We only have 9 because those are the only labeled images that got mapped to in. If all 36 got mapped to in, we would map 36. But you have to dynamically pick this number based on however many number of images got mapped, labels got mapped into an in. So we can run the model, same thing as up above, and we find that there were 449 correctly predicted. So let's look at a summary of what has happened here. And we find that the original model had 680 incorrect predictions at 95.9% correct. The 0O model initially had 697 correct predictions, and we moved it up to 741. It worked. By restricting the input set, we got a superior output set. It went from 75.2% correct to 79.9% for just these 2 letters. The in data set has a similar situation. We started with 459 images. Initially, we got 449 correct. After running the submodel, we got 449 correct again. That's an argument the submodel doesn't work. It's also a statement that we didn't have problems with in. It would be a different situation if we had run a Z submodel rather than an in submodel. But there's potential here for future work. Now, rather than continue to look at the data we trained the model on, let's do an independent test using our test data. This was provided in the Kaggle data. And so using the Kaggle test data, we can run predictions on the base model, we can run predictions on the 0O model, and predictions on the in model. And with that, we can see the summary total there. There were 3,241 images with 97.7% correct. The O0 model initially had 54 errors, and now it has 29 errors. So we improved it from 80.2% to 89.2%. So using the test data, this submodel does work. It improved our predictions. On the inside, it was interesting that initially it predicted all 87 in images correctly, and the submodel, of course, did the same thing. So there was no improvement on the in. Again, you should pick the correct letter for your submodel, but also it's an argument that maybe this version of the submodel will not be as effective. But overall, this has shown that by using a base model with all 36 images and then augmenting it with submodels with your problem data sets, your problem images, you can come up with a combined model that is superior.